from point A to B. So from point A to B, here you can see that circulate from A to B in direction of current. How the direction is? The direction is from A to B. Then the EMF across this particular inductance should be equal to minus LdI by dt. Now moving across an inductor opposite the direction of the current. This is EMF produced in opposite direction to the current, then the EMF should be given as plus LdI by dt. So these are the sign conventions when we have to take as a minus and when we have to take as a plus. Now, so far we have very clearly understood how and what are the role of resistance as well as what is the role of inductor in the circuit. Let us combine these two particular components, L and R. Now this is how we get it as an LR circuits, where which we have combined a component resistance and inductance in series with a source EMF. So this is a circuit containing a source E, a resistance with a value of R, and an inductance, self-inductance with a value of L, which are connected in series with the source through a switch key called as an S. So when the switch is open, obviously there will be no current in the circuit, but when the switch is closed, what will happen to the circuit now? The current will grow from its zero value, and this is the direction of the current in the circuit. The current is flowing through the resistance as well as the inductance when the switch is closed. We have seen the direction of the current. So without the inductance in the circuit, if just let us assume only R is there in the circuit and we have switched on the circuit, there is no inductance in the circuit, then the current will start its value from 0 to suddenly to its maximum value. Let us say that the I is the current in the circuit, I is equal to initially 0, and the maximum current in the circuit is I0. So instantly the current in the circuit will be I0. But because there is a inductance in the circuit, as the inductance is opposing the flow of or the growth of current in the circuit, the current in the circuit will be gradually increasing because it opposes. Because a back EMF is set up which opposes the growth of current in the circuit. So according to Ohm's law, suppose we take an V is equal to IR, and according to Ohm's law, what will be the equation? Equation will be E minus I into R minus L di by dt should be equal to 0. Isn't it? Earlier we have seen that E minus the potential difference across this R and also the voltage difference across this L. So E minus IR minus L di by dt is equal to 0. And for that, if you apply Kirchhoff's voltage law, so this is how we get it, like E minus IR minus L di by dt is equal to 0. So after mathematical calculations and integrating, saying that when time t is equal to 0, the current in the circuit was also equal to 0. So with that boundary conditions, if you substitute, finally we get it as an I is equal to E by R into 1 minus exponential of minus R by L into T, where we have taken as an tau as an L by R. We will understand what this is. So the final expression, the growth of current in case of LR circuit, after all the mathematical expression, we get it as I is equal to E by R into 1 minus exponential of minus R by L into T. What is E by R? E is the maximum voltage in the circuit and R is the maximum resistance in the circuit. So when we say that the maximum voltage and this is the maximum resistance, it means reciprocal of voltage and current, which are maximum, is nothing but the maximum current in the circuit. So same equation we can write it as I is equal to I naught into 1 minus exponential of minus R by L into T, where I naught is the maximum current flowing in the circuit. So now we have two conditions, and this, as we say that I is equal to I naught 1 minus exponential of minus R by L into T. Suppose this exponential of minus R by L into T is equal to 0, then what is T? The instantaneous time, we get it as an infinity. It means if T is equal to infinity, then we can say that I is equal to I naught. Only when the time is kept as an infinity, we can say that the I have reached to its maximum value as an I naught. Now we have two conditions. Let us understand the first. So as we have I is equal to I naught into 1 minus exponential of minus R by L into T. Suppose we derive it. The rate of flow of current, it means di by dt. So we will get it as in di by dt is equal to minus R by L into I minus I naught. This is V by R or E by R, maximum values. So this can be written as I minus I naught, or we can write it as di by dt is equal to plus of R by L I naught minus I naught. So this is the first equation saying that the rate of flow of current in the circuit di by dt is equal to R by L into I naught minus I. Okay. The second, if you say that this small t value, this is exponential value of small t, is given as in value as R by L, L by R. This small t, instantaneous t, if at all we gave a second value as an L by R second, then if we substitute over here, then what we will get? E exponential term. I'm just talking about the exponential term. Exponential term should be equal to minus t. Instead of minus t, we are writing it as an L by R and divided by L by R. So this entire will get cancelled. So this comes like exponential of minus 1, or we say that 1 minus 1 by E, or we say that E minus 1 by E. And what is the value of E? E is having the value of 2.718. So if you substitute 2.718 minus 1 divided by 2.718 into, this is nothing but an I naught. So then what will be I? I, we get it as 0.63 into V by R. So when the t value is L by R second, I will be equal to 0.63 into V by R, E by R. E by R is nothing but I naught. So the current in the circuit reaches to 63% of its maximum current when this tau is equal to L by R second. And as we said that the exponential term, this exponential term, when this is a 0, then only we can say that I is equal to I naught. So this is 0 only when the condition when t should be equal to infinity. So as we cannot keep the time as an infinity, the current in the circuit will never attain to its maximum value as an I naught. So if you follow this graph, this is I versus t, instantaneous t, and this is the curve when the tau is equal to L by R second, the current in the circuit reaching to a maximum of 63% of its maximum voltage. This is the maximum voltage. And the current in the circuit is never attaining to a maximum current in the circuit. Can you see that? This is the I is the value, red color, orange color, and this is the I naught value. So see, it will never reach to its maximum value. Because the current to reach its maximum value, this exponential term should be infinity. It means indirectly t should be, this exponential term should be 0. It means indirectly t should be infinity. So this is not possible. And we have taken this tau, and this is called in time constant, which is equal to L by R seconds. Units will be seconds. So current is trying to change when t is equal to 0. Inductor works hard as it needs to stop it. But when t is equal to infinity, current is steady, inductor does nothing. So this is all about the LR combination in the case of growth of current in the circuit. Let us decay. Let us allow the current to decay through the particular inductance now. Now what we did is we'll change a little construction. We have changed a little bit. This is a source, an R and L, which are as usual in series with each other. This is a switch S1 and this is a switch S2. So what we did, this is kept on, but here this is kept off. So when switch S1 is closed and S2 is open, current flows through RL circuit through S1. After some time, the current becomes the maximum value as in I is equal to V by R. Okay. Now what we are doing is we are keeping this switch S1 open and this S2 as in closed. So when switch S1 is open and switch S2 is closed, current flows through RL circuit through the S2. As this is open, no current will flow through this particular mesh. So the current direction will be only in this particular mesh. Earlier, if you have seen, the current direction was into this particular complete mesh, complete circuit. Though this was open, there will be a current because of this particular terminals, isn't it? But if I say that the switch S1 is open and S2 is closed, so the current is only flowing through this particular mesh now. Now this is nothing but we can say that we are allowing this particular current, whichever have reached to the maximum value, to its decay, through its zero value. So we can say that this is a decay of current in LR circuit, the circuit. So the current decreases, but the diminishing rate is reduced by the presence of inductor. Previously also I have said, if you have taken an LR circuit and switch on the circuit, the current will not shoot up to its maximum value because there is an inductor in the circuit, and because of the back EMF setup due to the inductance, there will be an opposite of flow. Similarly, if you have removed the source, and we have allowed this particular current to discharge now, to decay now through the inductance, it will not come to again a zero value. It will be gradually decreasing because inductor is present in the circuit. Now if you ask according to Kirchhoff's voltage law or second rule, what will be the equation? Do you have a source in this particular mesh? No. So what is the EMF value? It is a zero. So if you ask somebody what is the total EMF or effective EMF in the circuit, then it will be 0 minus IR minus LDI by dt should be equal to 0. Isn't it? Or we can say that minus LDI by dt or minus IR is equal to 0. Now on integrating and applying the boundary conditions as t is equal to 0, the current here, when the time t is equal to 0, the current in the circuit was maximum. So when t is equal to 0, the current should be maximum. I should be equal to I naught or I should be equal to E by R. So with that condition, substituting that condition and doing little mathematical steps, we will get as I is equal to E by R into exponential of minus R by L into T. Earlier it was I is equal to I naught into 1 minus exponential term, but here we were getting as in the current in the case of decay current, decay I is equal to V by R into exponential of minus R by L into T, and this E by R is nothing but maximum current. So we can say that I is equal to I naught into exponential of minus P by tau, where we say that tau is nothing but what we have taken as an L by R seconds. So we can write equation as I is equal to I naught e to the power of minus T by tau. So current decreases as time passes, but not instantaneously to 0. It opposes, so it will never come to a 0 instantaneously. This is due to the inductor or resistor's change. So this was the equation. We got it as I at its instant value t should be equal to I naught into exponential of minus t by L by R. So if at all this small t, which is called as a time constant, is substituted as R by L second. So what will happen? R by L divided by L by R. So this all will get cancelled. E to the power of minus 1 we will get it. So e to the power of minus 1 is nothing but 1 by E. And E you have the value of 2.718. So 1 by 2.78 you will get it as 0.37. Okay. So now the maximum current in the circuit is decaying exponentially, as you got it in the equation as I is equal to I naught into exponential term. It means it is not suddenly falling to the value of 0. It is decaying. This is how we can see it. It is decaying, and this is the value. This is the value of current when we say that small t is equal to L by R second. Small or tau is equal to L by R second. It means the current in the circuit reduces to 37% of maximum current when the time constant is equal to L by R seconds. As this is a time constant, the unit for this is in seconds we need to measure it. Now let us understand the capacitor, because we have exclusively understood what is resistance, what is inductance, and then we have applied inductance and resistance in series with each other, and we have seen what will be the growth of current as well as decay of current in the circuit. So now we will understand the component called capacitor, which we earlier also defined as has an ability to store an electrical energy or electrical charge, can be called as a capacitor, and capacitor blocks the passage of DC and allows the AC current to flow it, and also opposes the change of voltage in the circuit. And see here, this is a two equal parallel plates is a symbol for capacitor. This is plus Q. This plate is charged with plus and this is minus. Whereas here you can see that this is plus and this is minus. So moving across a capacitor from the negatively to positively charged plate increases the electric potential. So del V will be equal to VB minus VA. And moving across a capacitor from the positive to the negative plate decreases your potential. Here it was negative to the positive, and now this is moving across the capacitor from the positive to negative plate decreases your potential. If current flows in that direction, the capacitor absorbs power or store energy. That's how the energy is stored into the capacitor. And here we can say that the potential difference across these 2 points V del V is equal to minus Q by C, because it is moving from positive to negative plate. The current is moving from positive to negative. If you see here, it is moving, the current is moving from negative to positive, then del V was equal to plus Q by C. Whereas if the current is moving from positive to negative plates of the capacitor, then del V should be equal to minus Q by C. So what is the power absorbed? Power is nothing but voltage into current. So I into del V, or we can say that what is I in terms of charges? I is nothing but the rate of flow of charges. So this we can write it as dq by dt into del V is what? Q by C. So we can write this as d by dt of q square by 2c. And what is half q square by c? Is nothing but an energy. internal energy. So we can say that the power absorbed is equal to du by dt. Let us understand the discharging a capacitor. So when the direction of the current flow is towards the positive plate of a capacitor, then I is equal to plus dq by dt. Similarly, when the direction of the current flows is away from the positive plate of the capacitor, it means it is from negative to positive, then the current in the circuit will be I is equal to minus dq by dt. So what is minus dq by dt? The rate of flow of charges, it is in minus. It means the condenser is discharging. Plus dq by dt, we can say that the condenser or capacitor is charging. And when we say that it is minus dq by dt, it means the capacitor or condenser is discharging. So this is a basic definition or basic understanding about the capacitor. Now let us understand, if we take a resistance component and a capacitor component connected in series. So we can say it as an RC circuit. The capacitor is neutral, no current flows through it because the switch S is open. So what we did, we have taken a source EMF E, condenser with a value of capacitor C, and resistance value is in R, and this C and R are connected in series with a EMF. Now let us understand, after the construction, let us understand the principle of this circuit. What will happen? Earlier here the switch S was open. Now what will happen when the switch S is closed? You can see the current is flowing in this particular direction. It is flowing through the condenser, you can see in this particular direction. So when we say that, when this particular switch, or it can be called as a Morse key because it's a two-way key. When this particular switch is connected to, or when this switch is closed, the charging on the condenser takes place until the potential difference across the plates of the condenser becomes E. When we say that the condenser is fully charged, if the potential difference across these two plates of the capacitor or the condenser is equal to the applied voltage, then we can say that the condenser is fully charged. So even if it is fully charged and we have kept the switch as enclosed, it will start opposing. Then it will start opposing because it cannot take more than that. So simply when we charge a battery at our house, like especially for the mobile battery, once we see that, graphically we can see that on the battery whether it's how many percentage it have charged. So once it is fully charged to its maximum value as 100%, there is no meaning of keeping the circuit on, because it will be opposing the further flow of current through the condenser. So we say that in the process of charging the condenser, the battery tries to introduce more and more charge on the plates. But the charge already attained by the plates opposes the introduction of further charges. So what is happening? Once it has attained to the maximum charge, it will start a back EMF. It will start opposing the further flow of further charge on the condenser. So we can say that a back EMF is set up in the circuit. So this back EMF setup in the circuit, or back EMF because of this particular inductor, decreases the rate of charging of the condenser. So now you can see that here in this circuit, plus Q goes to lower part of the charge, plus Q is repelled from the upper part of the capacitor, leaving a minus Q charge. As the lower plate increases in plus charge, current decreases due to repulsion. So this is how it happens, and this is how we can say that a back EMF is set up. This process repeats until the capacitor gains an EMF equal to E and plates with charges plus Q and minus Q. Finally, the current is zero due to maximum charge repulsion. So when we say that it is maximum charge, it is fully charged, the current will be zero. So we can say that the maximum charge, so Q should be equal to what? C is the capacitor value. So C into E, we can say it as a maximum charge in the condenser. So we can also say that Q naught is equal to C into E. Now if we apply the Kirchhoff's law into this particular RC combination, we can see that as it is opposing, so E minus Q by C minus IR should be equal to 0. Isn't it? Q by C is the charge. This is the voltage drop across this particular condenser which is opposing the main source. So it is minus Q by C minus IR according to Ohm's law. This resistance is opposing the growth in the circuit. So this is according to Ohm's law, it's equal to IR. So E minus Q by C minus IR is equal to 0. So you got the equation. Now this, because we are finding out the charge in the condenser in the combination of RC circuit, this I we will replace with respect to Q. So what is current? How we define the electric current? Electric current is nothing but rate of flow of charges. It means d by dt of Q. So we can write the same equation as E minus Q by C minus dq by dt is equal to 0. So this is a differential equation where which we just substitute, rearrange the things and we integrate, and after integrating we will apply the boundary condition saying that when the time t was equal to 0, what was the charge value in the condenser? It will be 0 obviously, because it was not having any charge into the condenser. So initially when time t is equal to 0, the Q value on the condenser should be equal to 0. So applying these two boundary conditions, you can find it and get the final equation as E minus, because the equation is E minus Q by C minus dq by dt into R is equal to 0. So if you solve it, you'll get it as Q is equal to CE 1 minus exponential of minus T by CR. This finally we get it after solving few mathematical steps. Q is equal to CE into 1 minus exponential of minus T by CR. What is CE? Maximum charge value, maximum capacitor value, and maximum source in the circuit. So C into E is nothing but Q. So we can say that Q is equal to, instead of C, Q is equal to capital Q. This is a Q or Q naught, we can say it. This is nothing but the maximum charge in the condenser. So small q, you got it as Q into 1 minus exponential of minus T by CR. And the other equation is in the form of current. So I is equal to E by R into exponential of minus T by CR. So this is the equation, you got it. This means at t is equal to 0 seconds, charge in the capacitor is 0. As time passes by, charge in the capacitor increases up to its maximum value as in CE. So here you can see, or in the later slide you can see here. Here only. So this is charging the condenser. You can see that. So when we keep this tau, a time constant value as an RC, and this again RC can cancel e to the power of -1. So the same way what we did in the case of LR combination, this will come like 0.63. It means the charge on the condenser attains 63% of its maximum charge when the time constant value is equal to RC second. And as this exponential term is equal to 0, then only the charge on the condenser will attain to a maximum charge value. So which is not possible because t we cannot keep it as an infinity. So if you observe this graph, this orange line will never attain to a maximum charge value as in CE. This is maximum charge. This is 0.63 into CE, 63% of its maximum charge. So this condition is there when tau is equal to RC seconds. This you can see here, the same circuit in the case of charging and discharging even. This is the equation what we have studied, the same equations. Q is equal to Ce into 1 minus exponential of minus t by tau. And in terms of I will be equal to I naught into exponential of minus t by tau. This was the charging. Let us understand the